So this is a game-changing topic, interleukins or cytokines. This is very much important in rheumatology, and it differentiate all the immune response of the body. And generally I have seen a lot of posts regarding this, and there is a post in which an orthopedic surgeon is earning a $300 for dealing for bones, and a rheumatologist is dealing a almost $3 million. So there is a meme regarding this interleukins and cytokines. So they differentiate the two doctors, that as hard work behind learning and functioning of the interleukins and learning of bones is very much differentiating. Like a surgeon dealing with bones is earning less than a rheumatologist who is dealing with cytokine and interleukin. Is way more high earning of him. So let's discuss interleukin first. Generally we describe interleukins from the different source of production. So first of all, macrophages. We have the APC macrophages, and they release interleukin 1, 6, 8, 12, and TNF alpha. So just learn this by heart, so that whenever the question is asking you for this cytokine it is secreted from which cell, so you have a mindset that this cytokine belongs to this source, and that cytokine belongs to that one. So macrophages release 1, 6, 8, 12, and TNF alpha. And the next one, we have all the T cells. They're releasing interleukin 2 and 3. Afterward we have a T helper 1 cell, and it releases interferons gamma, and T helper 2 cell releases interleukin 4, 5, 10, and 13. So we have 1, 2, 3, 4, 5, 6, no 7, 8, no 9, 10, 13, 12, and 13, and TNF alpha and interferon gamma. So first discuss I will describe the most differentiating interleukins and their function. And there are also I have seen a lot of extra interleukin functioning and interleukins in the UWorld descriptions. So they came in the distracting answer, but they are not very much high yield than these interleukin described in page 108 in first aid. So first we will discuss macrophages, the interleukin which are released from macrophages. First one is interleukin 1. So interleukin 1 is very much important in acute inflammation. They causes pyrogens, or they can cause fever. They are in acute inflammation. They can activate endothelium to recruit WBCs to the site of inflammation. And they also known as osteoclast activating factor. So if the osteoclast activated, then the bone get reabsorbed. So it's the interleukin of acute phase reactant interleukin, which is related to sepsis and fever. So interleukin 1 done. Next one is interleukin 6. Interleukin 1 is done. Next one, interleukin 6. Interleukin 6 is also related to, it's a interleukin of acute phase reactant, and it is in fever, sepsis, and acute phase reactant, Q's phase reactant interleukin. So interleukin 6 is releases when there is an inflammation, when there is increased ESR. Then we whenever a person is asymptomatic or it's having a unusual low grade fever, and there is no any a medical cause for that disease, then we will do a test known as ESR and APR, acute phase reactant and ESR, and this test detect that either there is an inflammation in the body, or the body is non-medical cause of inflammation, febrile illness or febrile illness, or inflammatory or non-inflammatory. So interleukin 1 and interleukin 6 and ESR is very much important in detecting those causes. Then we have another characteristic of interleukin and another function of interleukin, that it increases the growth of T and B cell growth. This is an extra function which described in the Uval diagram. Next we have interleukin 8, and interleukin 8, it is a major chemotactic cytokine for neutrophil, and interleukin 8 is very much important for chemotaxis of neutrophil and the site of inflammation. Then we have interleukin 12, and interleukin 12 is related to differentiation of activation of natural killer cell activation, differentiating T helper 1 cells, which can releases further interferons which kill intracellular bacteria, intracellular pathogens. It can also facilitate, not induce, not activate, just facilitate formation of granuloma in TB. So focus on this, facilitate. Then we have TNF alpha, tumor necrosis factor alpha, and in TNF alpha it is it activate endothelium released from macrophages. It causes recruitment whenever the endothelium is activated. It releases adhesion molecule which can cause recruitment or diabetes, I guess the terminology, recruitment of WBCs, which can causes capillary leak, edema, inflammation, etc., etc. So it can also activate, it can also cause cachexia. TNF alpha go to the hypothalamus, inhibit the appetite, which can inhibit the LPL, and that LPL I will discuss later. I will tell you later. Cachexia in malignancy. So what was I discussing? I discussed that TNF alpha go to the hypothalamus, inhibit the appetite, and also inhibit LPL. That LPL inhibition can cause phosphorylation of serine and threonine of insulin receptor, which can causes insulin resistance. So TNF alpha is also causing insulin resistance. It can also cause cachexia. It can activate it is also acute phase reactant, causes sepsis and fever. It also causes maintain, the word maintain is important, maintain granuloma of tuberculosis. So we have here all the interleukins, and activate endothelium it's a part of inflammation, so it increases inflammation. It can maintain granuloma, So it's cell mediated immunity. So this is all the functioning of TNF alpha. We have the TNF alpha inhibitors, infliximab, adalimumab. These are the monoclonal antibodies which inhibit the TNF alpha and inhibit all these functions. And the TNF alpha inhibitors are important in controlling these conditions. First one is psoriatic arthritis or psoriasis. Then we have ankylosing spondylitis, inflammatory bowel disease, arthritis or inflammatory bowel disease, and R is rheumatoid arthritis. So after this TNF alpha, we'll discuss T cell, interleukin 2 and interleukin 3. So for all T cells, they release interleukin 2. Interleukin 2 has a very short line but having a very differentiating features. Interleukin 2 activate B cell growth, interleukin 2 activate macrophages, interleukin 2 activated T cell, all the T cell, regulatory, helper, cytotoxic, all one. So T cell regulatory, then CD8, CD4, CD or the cell receptor. So that's why I'm talking T cell 1, T cell 2, helper, and all these. So these three B cell, macrophages, and T cell, they activate this part: B cell growth, macrophages activation, and T cell differentiation. And then interleukin 3 can cause hemopoiesis, means it stimulate bone marrow cells, stem cells, and cause the release of increase like our erythropoietin GM-CSF, which can cause increase the production of WBCs, interleukin 3. Next we will discuss afterwards we have T helper 1 cell releasing here T helper 1 cell releasing interferon gamma. Interferon gamma, when I was researching about interferon gamma, I came across a lot of new factor. Interferon gamma is a glycoprotein, and it is released by an infected cell. When a cell is infected by a virus, then it releases a glycoprotein. This glycoprotein para or auto releasing autocrines, which prime the neighboring cells. I am just explaining the mechanism. Paracrine or auto, it releases the autocrine which goes to the neighboring cell and halt protein synthesis of the neighboring cell, like it attacks the machinery, nuclear machinery of the cell, neighboring cell. Whenever the protein synthesis is inhibited, like by the nucleosomes or DNAs, etc., then the infected virus cannot replicate in the cell, and TNF alpha, TNF gamma, they protect the body in doing so. So when the virus is not replicated, it just reside in that cell. Also TNF alpha increase MHC expression. When there is APC expression, the antigen presentation increases, and there is a cascade of release of T cells, which can causes the which causes virus to cytotox or to be dead. Then we have then we activate antigen goes to natural killer cell, and they secrete interferon gamma. Likewise, APC or macrophagic interleukin 12 goes to T cell, and which they release interferon gamma. Then this interferon gamma activate macrophages, like it enhances its activity. It also activate natural killer cell to increase the intracellular cytotoxicity, killing of the intercellular pathogens. So it can also activate whenever the macrophage is activated, they can cause granuloma formation. So this is all the mechanism of interferon gamma, and then we have T helper 2 cell. T helper 2 cell releases interferon, interleukin 4. Interleukin 4 increase IgE production. How? By increasing B cell growth. And how B cell growth happen? It happen by increasing T helper 2 cell differentiation. Also it can increase the production of IgG, but that is a pretty less yield than IgE. So it is involved in IgE production. Then we have a relatively similar interleukin 13, which can increase the production of immunoglobulin E from B cell. And interleukin 13 is present in first year 2021, not in 2020. So that's why they just added this new interleukin 13. And then interleukin 13 also activate the alternative macrophage activation, induces the alternate macrophage activation. Then we have interleukin 5, and it does IgA production, increase the IgA production. It also IgA production, how? IgA class switching, IgA production, increase the cell growth, and also it is stimulate and production of eosinophils. Then we have interleukin 10, last one, interleukin 10, and T tumor growing transforming growth factor beta, they A10 innovate immune response by decreasing MHC expression, by decreasing T helper differentiation, by decreasing macrophages, and also it is also released from it is released from T helper 2, also released from T regulatory cell. So this is all about interleukins, and it's very much high yield topic, and it is the game changer of the emerging field of rheumatology.